video lecture on energy. So, when we have energy, when we think about it, when we talk about it, when we see the word, what exactly comes to mind? So, one of the things that we usually think about is electricity, light. What powers our computer? Computer uses energy, and energy costs money. Electricity costs money. But where exactly does this energy come from? So it comes from probably a hydroelectric generator, or maybe from a geothermal generator, or maybe from even a nuclear plant. But all these things have something that causes motion that generates electricity. So there's motion, movement, or at least in the case of nuclear plants and geothermal plants, there's chemical energy. So, or well, as the word says it, nuclear energy. Okay, but that is like an energy that is there, and that we use it, we extract it, but it's not something that exactly like we would think is moving. But it's energy. Deep down inside a thing, there's things moving in there, very fast, very quickly, very powerful. And that's something we'll see at the end. Power. Okay, but let's go on to the physics. What exactly is energy? Well, by definition, it's the ability to do work, or maybe the capacity to do work. But does that really tell us what is energy? I mean, it's not exactly something we can touch. So therefore, it's actually, we don't know what is energy. We just know that it's there and it allows movement of things, transfer of things. But other than that, we don't really know much about it. We even call things in the universe dark energy. What does that mean? Oh, it's the portion of the amount of energy that we see in the universe that should be there, but that we can't see somehow. The missing energy in the universe. So energy is used a lot, but it's all related to movement. So when they say the energy of the universe, it's actually trying to take an estimate of the energy of all the things moving inside of it. And everything is in motion. There is no such thing as something steady in the universe. It is expanding. The universe itself is not steady. Okay, but then we can classify energy into different types. Now, I mentioned chemical energy. We're not going to explore chemical energy, but we are going to explore kinetic and potential energy. Now, I was talking about movement. So, kinetic energy is associated with this energy of movement or motion. It's the energy of motion. And potential energy is, for example, when we have something that is about to move or something that can move, but maybe a force is impeding it to move. So, there is energy being spent. Okay, and also something that we'll explore later how it works is that kinetic energy and potential energy can convert between each other. Okay, so potential energy, so think about it like an explosion. It's steady there, it has a bunch of potential energy because it's about to explode. It just needs an ignition, and once it ignites, everything starts zapping out at really high speeds. Okay, so you went from chemical and potential into kinetic energy. So energy can be converted between those two. And also, you have the case of E equals mc squared. So E equals mc squared means that the energy is equal to the mass at rest. So it means that it's not necessarily a mass in motion. Speed squared. Okay, so even if you're not moving and you don't have any kinetic energy, you actually do have some energy. You have some rest energy. Okay, but look at the beautiful waterfall over here. Things are in motion. Things, and how does it come into motion? Well, it falls from a height. Okay, so even if you place something up there, it will fall down. We know that. And that'll move, therefore it'll have kinetic energy. Okay, how fast it moves, well, that probably depends on how high it is. Okay, so kinetic energy. Anything that has motion has kinetic energy. So, and this kinetic energy can be vibrational. Okay, and there's several forms of vibration, but every time you think about waves, that's probably caused by a vibration, or most likely caused by vibration. Now, if you notice a string, the string has a certain form of a wave. And it goes and it comes back. That's a vibration. We also call it harmonic motion. But as you can see, once he applies the necessary force for it to move, the energy of it will make it to keep on going and going if nobody stops it. We also have rotation. So the rotation of the Earth is a good example of this energy. Now, why? Because, well, everything around Earth's axis is rotating in a circle. It's not moving along a straight line. So your point in absolute space is not along a straight line. But you're also rotating around the sun. And that's the one that we call translational. But in the case of our class, we're just going to base ourselves on the translational along a straight line. So imagine Voyager heading out of the solar system. Well, in reality, it's not in a straight line, but let's just say it is for at least short periods of time. Okay, so translation is basically moving along a line. Now, this line doesn't have to be just left or right to left. It can be up and down. However, we're going to focus on left to right. Okay, therefore, we're going to use delta x instead of d. Now, if we go back to the definition of work, we have that the work is equal to the force times the distance or displacement times the cosine of theta. Okay, and if we're just talking about a straight line along x, then we can just say that the cosine of 0 is delta x. Okay, and if you recall that the force is equal to ma, mass times acceleration, Newton's second law, then we can replace that into that, and we have that the work is equal to ma times delta x. And the a times delta x, we can further replace it. Okay, now what exactly are we looking for? So we want to have this work in terms of the mass and velocity. Okay, and why velocity? Because that describes motion. So how do we do that? Well, we use one of the kinematic equations where Vf squared is equal to Vi squared plus 2a delta x. And this allows us to calculate the acceleration times the delta x. So once we replace the values, we divide the Vf squared minus Vi squared divided by 2, then we get a delta x, and we can replace that. And then we have an equation for work that is based on mass and velocity. Mass and velocity. And the mass doesn't change. Not in our cases. Okay, so what does this 1/2 mv squared mean? Well, we can define the kinetic energy as 1/2 mv squared. So we have the mass times the velocity squared. Now there's an important thing here. Has to do a little bit with some vector math. But basically, we went from having a quantity with the vector, so the acceleration and the acceleration and the delta x are two vectors that multiply by each other and gave us a velocity squared. This is not a vector, this is a scalar. Okay, so remember that. And then, okay, the kinetic energy is 1/2 mv squared, and we can define it also as our final. So here's our final, and here's our initial. Okay, those two are the KEs. KE. KE final, KE initial. The units that we use are joules. Okay, we keep, so if the work is equal to a difference between the final and initial kinetic energy, it has to keep the same units. Now, even if you want to double check it, so let's double check it really quick. So mv squared, so the units of mv squared is kilograms, mass squared, second squared. The units of FD is newtons times meters, and newtons is kilograms, meters per second squared times meters. Okay, so they give the same. So you see, joules. Now, let's talk about potential energy. So potential energy is something that can make something move, but usually we just take it into account as a difference in its position. Okay, an energy that is caused by a difference in its position, by a change in its position. Okay, a point relative to another point. Okay, for example, Bose. Look closely at her motion. She picks the boat into the back, and then that allows the arrow to go really fast outwards. Okay, so this is actually elastic. So because of the elasticity of the string in the boat. We can also have the case of, say, a diver. So a diver goes really high and then he jumps. Now, remember that according to the kinematic equations, so the Vf squared is equal to the 2Gy from kinematics, and that means that the speed is going to be faster the higher you go. Now let's look at another case. Springs. Now springs, when you compress them, they're gonna try to stretch out, and when you stretch them, they're gonna compress. So either way, you can store energy in the spring. Okay, so we have three cases of potential energy. Right when the girl is about to release the arrow, when we have the diver that is about to jump down, and when you compress or stretch the spring. But notice that if you want to calculate things, you always have to do it relative to a certain position. Okay, so how can we classify them furthermore? Well, we have gravitational potential energy. So this is a result of how far away you're from the Earth or the height. So if we have planet Earth, okay, your delta y from the Earth. And if your y initial is 0, then you can say that your yf is your height. Okay, and the further you are, the more gravitational potential energy you're going to have. Okay, and elastic potential energy is similar to it, but there is something that keeps it from going further, and that is going to be related to the amount of the stretch. Okay, so the energy is related to how much you stretch it or compress it. Now remember that real life springs break up or they deform. Okay, but this is an approximation. So how do we actually calculate these things? Well, the gravitational potential energy, if we go back to our equation of work, and we replace D with delta Y to signify that we're dealing with vertical motion, okay, and then we have F delta Y. And the F is going to be the force of gravity, which is mg. Recall that G is 9.81 meters per second squared, and G is positive. Okay, the acceleration is G is positive, but obviously this force is directed downwards. Okay, but when we replace this back into the work, we have mg delta y, and then we have mgyf minus mgy initial, and we can say that mgyf is a height, then we have our potential energy. And we say that the potential energy, gravitational, is equal to mgh. And if you want to keep all the variables, then you have final potential energy minus initial potential energy. Okay, so this is a case of gravitational. But what about elastic? So elastic, we have this force that describes springs. Now this was discovered a little bit before Newton came along by Hooke. And Hooke saw described this force experimentally, and he saw that each spring has a spring constant. So K is a spring constant. And it is in newtons per meters. Notice that it has to be in newtons per meters because we have a delta x. So if we replace that into the equation for work and we do some calculus, some integrals, because unfortunately there is not another way to do this to calculate the work, we simply take the results from other guys, and we have that the potential energy is equal to 1/2 kx squared, the elastic potential energy. And this is pretty much the potential energy you'll use in a spring. And notice that the delta x is squared. Okay, so we have newtons per meters times meters, and we have newtons meters. So if we want to do the units, we have newtons meters times meters squared. So this is Newton meters, which is joules. And in reality, this x, you have to be careful with this x. So look at the diagram here. This, what it calls the extension here, this is going to be your x, okay? So you can have an xi and an xf, okay? This is why I write Hooke's law with the delta x. So we have the xf minus the xi. and the force will be given opposite to the movement, so to the move that you have. Okay, so the force, if you go down, is like this. Okay, the force goes up. That's why. So, but you'll have a negative in there because um the so according to the ruler, the xi is smaller than the xf. I mean the xi is bigger than the xf, so you're going to negative, which cancels out with the negative. That gives you a positive force going upwards. Okay, so this gives us the elastic potential energy, which is 1/2 kx squared. Also, remember, when the spring is at rest, when there is no forces acting on the spring, we say that it is at equilibrium. Okay, this is when it's at equilibrium. That's going to be your x initial. Okay, so if you're using delta x, then xi will be when it's at equilibrium. And then your xf will be the stretching. So your x is actually a difference. Okay, so be careful with that. Now, what about mechanical energy? Okay, so what is mechanical energy? Well, it's basically the energy due to the position or movement of the object. You can have both. That's the thing. So mechanical energy is actually a sum of the kinetic energy and the potential energy. Okay, so think about it in this case of the roller coaster. So the roller coaster reaches the maximum height. So it's at h. And then, so from the height, then it goes really, really, really fast. And it reaches a maximum speed when it's downwards. Okay, so at height, ground, you have the velocity. Okay, and you actually have the velocity all throughout here. Okay, so but at doing this point here, this is when the potential energy is being converted into the kinetic energy. When that happens. And then the maximum kinetic energy, so the Ka max, will then transform into potential energy when it goes up. But it's obviously going to stop at a certain point if it just keeps going up. Okay, that depends on the amount of kinetic energy. So we say that the energy is conserved. Okay, so our initial kinetic energy is going to be equal to our final kinetic energy. And we can write this into a single equation. Okay, so we write that we have the initial kinetic energy. The final potential energy is equal to the final kinetic energy plus the final potential energy. Okay, so we have the initial energy and we have the final. And we can furthermore write this in two other quantities. So if you and you can even cancel out the m's if you look at it. So you could even cancel out this if you wanted to. So that means that in terms of the velocity, you can calculate the height of an object, which is the velocity and the acceleration which in this case is going to be g. Okay, so this is a really powerful equation, and it's actually used, although not in the same form, throughout pretty much all of physics. Okay, conservation of energy is it's not only a useful trick, it's pretty much one of the basic laws that keeps everything working the way we have. Now imagine the case of a pendulum. So a pendulum, when it's at its maximum height, it's barely moving, and then it starts to fall down again. And when it starts to fall down again, it goes really fast, such that at the bottom point is where it has a maximum velocity. And then the minimum velocity equal to 0 is at the top. But at this point, at the top, you have the maximum height. Okay, so therefore mgh, and then here 1/2 mv squared are the two quantities you're going to use. So what is the basic equation of a pendulum? Well, 1/2 mv squared equals to mgh. Cancel out the m's, and you have that v squared is equal to 2gh. Therefore, v is equal to square root of 2gh, and that is the maximum velocity you'll find out in the case of a pendulum, only depending on its height. Now, back to what we were talking before about powerful. So when you hear that a car has, 200 horsepower, what exactly does that mean? Well, horsepower is actually a unit of power, and power is the rate at which work can be done. This rate depends on the time, so how much work you can do in a certain amount of time. What is the equation for power? Well, we have work divided by delta T. That is all. So basically, the change in energy divided by time. The change in kinetic energy or the change in potential energy divided by time. And joules per second, we use watts. Okay, the units of power is going to be watts. And if you want to remember something, is that 1 horsepower is equal to 750 watts. Okay, and you'll usually see an electricity bill that, you consume so much kilowatts hours. Okay, that is actually, so if you think about it, that is like power times time. And power times time is simply energy. So they're telling you how much energy, but instead of using joules, that you're consuming. Then we can also use, instead of writing W over T, we can go back to the definition and write it divided by delta T, and that's going to be equal to F times V. Now, if you think about it, this is so what is how much force you apply and what is the velocity that comes out of it? Okay, depending on the power that you have and the force, you can get a certain velocity. Now, this is actually pretty important later on to calculating like what is the maximum speed probably a car can reach. So say that the force that you need to apply to move the car is the weight of the car, and the power is a horsepower. So you divide a horsepower divided by the weight of the car, and you get the velocity. So say velocity. So a car, the velocity would simply be the power divided by F. Okay, so say the horsepower divided by the weight of the car. Now, obviously, in real life, you have to take other things into account, like, for example, the tires, with the floor, the friction, the wind resistance, but this is a basic approximation. Okay, so maybe, so depending on the horsepower and the weight of the car, you can calculate what is the top speed. Now, if you want to calculate what is the acceleration, there you have to do some other math. But it's not impossible. So, that is all for energy. A quick introduction. Fortunately, we're not going to be doing any problems on this unless we return back to classes. But we're going to work on more simulations. to represent the laboratory. So you're going to use computers as your laboratories. And we're going to review some more problems that we've done on work, and we're going to go back all the way to kinematics for some problems. All right. I'll talk to you guys soon again.